That one has some.
How to let me try. Yeah. Let me try. Do. Okay. And I just need to put it in my pocket, right? Hello. Yeah, it works. Are there any laser jet? Yeah. Oh, cool. Let me check here. Yeah. Okay. Cool. It works. Okay. Hello. Yeah. The Central Time. And this is Junyang from Nvidia, and I'm happy to be here to represent the team to make the sharing of the Hopper supporting Triton. And actually, this is teamwork, and yeah. So firstly, I want to make some acknowledgement, and this work is actually a very great joint effort between NVIDIA and OpenAI. And this is a snapshot for the module request of Hopper Triton support, and all the people working on this project are listed here. And this is a very nice teamwork. And my sharing is organized as following. Firstly, I will recap Triton background very quickly, and then I will talk something about the motivation for us to do the Triton Hopper support. And next, we will go through some key Hopper features and what challenge it brings for Triton. And next, we will discuss some details such as the dialect design, the path pipeline design, and something like that. And next, I will show some performance number. Finally, I will conclude with the final plan for the future. Okay. And here is a very interesting slide I borrowed from my colleague Gustav. He tried to compare CUDA with Triton, just the echo field comparison. But here I just make the analogy that CUDA is something like a professional camera. You have a final control. You can control everything you want, and you have a lower bound for performance, but a higher bound for performance. And the Triton is kind of like a point and shoot camera, and you have less knobs, but it's more convenient, and it provides a better trade-off between the productivity and performance. So the lower bound for performance is higher, but usually the higher bound is lower. So they are targeting different scenario. Actually, these two things are complementary to each other. And yeah, here is a very vivid example to show the feeling of Triton. I think most people in the room are very familiar with that. And we just can use tens of lines of Python code to write a feature kernel, which might require handled code of CUDA. Yeah. And here I just try to zoom in a little bit and try to demonstrate some idea when we try to solve in Hopper. And here is a jam example. And I just highlighted the data loading operation with green color and the data loading operation in green color and the computation operation in yellow color. And we can see that for Triton, we just need to write the entire logic in higher level language. But the compiler can do some clever things, such as we can just lower the Triton Python DSL into the IR sequence, and then we can load them into the corresponding PTX instructions. And this is for Ampere. And for Hopper, actually the compiler will do the similar things, but we want to lower into the Hopper-specific instructions there. And the reason for us to want to add the Hopper support for Triton is very straightforward. Hopper brings very good value for performance, and it brings at most 6 times computation improvement compared with the Ampere, and also it brings 2 times of the memory bandwidth improvement. So we want to utilize the power, but also we don't want to bring too many additional complexity for users. We want to make sure the existing user kernels can be utilized directly. So that's some design principle we need to take into consideration when we add the Hopper support. And here I just try to list some concrete challenges and to show what we are considering here. I can move there. We should cover both audience. Yeah. So there are several concrete challenges we need to handle. The first one is about the hardware features. And also there are some software things we need to handle. And for hardware features, there are some key things introduced in Hopper. That is the TMA, which is specific for data loading and storing. And we also introduced the warp group GMMA, which is a coarse-grained tensor core, which can provide a better mass throughput. And we also introduced the distributed shared memory support in Hopper, which can share the data between different CTA belonging to the same CTA. And when we support these new hardware features, we want to minimize the changes with the front-end API because we want to make sure there are decent backward compatibility. And also with the changes of hardware architectures, there was some new software paradigm become more dominating. For example, warpization is more and more important for Hopper-style architectures because the gap between the computation and the memory access become more and more significant. We need some software tricks to try to hide the data loading latency. Yeah. So all these things need to be considered to support the Triton Hopper. So we just make some minor changes with front end. When we say minor changes, it means that we just add a new load store API, which is the make block point API. But this API actually is incremental to Triton. It means that you don't need to use that. But the only loss is that you might not be able to utilize some Hopper features. So it's an incremental front end changes. And also we support the programming on CGA, which we will talk about later. And of course, we introduce some new operations into the Triton dialect and the Triton GPU dialect. And because the Hopper is relatively new, so the community LVM, MIR, and LMIR is still in lack of the Hopper instruction support. So we just enhance the backend to support the Hopper specific instruction there. And also the path pipeline have been enhanced significantly. We add a plan CD path to do the tiling from CJ to CT carefully. And also we need to add some backward compatibility path to make sure for some new API, it can still work for old generation of architectures. And also the existing path pipeline need to be adapted to the new hardware. And also finally, we add some passes to support the warp stabilization logic to try to make it as automatic as possible. Okay, so next, I will go through some key features one by one and with some details. First one is about the CG and the distributed shared memory. And for GPU, actually, before Hopper, usually we will split the workload into several CTAs and then distribute it to the GPU, try to parallelize the computing resource. And for Hopper, we introduced a new hierarchy called the cluster or CGA, which consists of several CTA inside. And with that, there are some benefits. For example, all the CTA belonging to the same CGA can access each other's shared memory simultaneously. Also, when we try to load the data loading can be shared between different CTAs. With that, we can utilize the memory data path more effectively. This is important. But this is a little bit complicated for users to use. You need to use some new hardware instructions. You need to configure some flags very carefully. So it's very boring for ordinary users. So when we design the Triton Hopper support for these features, we just try to introduce as minimal front-end changes as possible. We just introduced a new performance knob called the num-CTs, and when you specify it to be 1, it means that it just fall back to the ambient style kernel. But when it's greater than 1, it means that we want to demo the CG and the distributed memory. And the Triton compiler will handle all the things under the hood to try to automate everything. And the next one is about TMA, and for TMA, actually, it's a new hardware unit. We try to do the data accessing and in coarse-grained way. And before Hopper, when you use the right kernels, you need to compute the memory access logic carefully, such as the address you want to access, and you need to handle the out-of-bound data accessing and something like that. And it will put more pressure for the instruction issue, and also put more pressure for the scalar instruction unit. And with Hopper, because we have a dedicated hardware to do the data operation, so we can just configure it with some metadata information, and then send an asynchronous instruction to the TMA instruction unit, and then we can do other things and check the status to synchronize, and then we can get what we want. With that, actually, we can just save significantly of the data loading, data storing overhead there. And to support that, we consider to introduce the new API. The reason for us to introduce API is very simple, because for compiler, if we can just see the above fine-grained APIs, it means that we need to introduce some graph passes to try to analyze and extract the information and assemble them to fill into the TMA, which is workable, but which might be not robust enough because when you need to analyze some ad hoc IR sequence, it's easy to have some corner cases. And by introducing a new API like the make pointer, when you create the pointer of point to tensors, you just need to specify the base address, the shape, stress, and offset, and something like that. And then this structure information will be kept and passed to the compiler backend. And it will make the compiler life a little bit easier to do the mapping to the TMA hardware. That's why we introduced this API. And also there is a rewrite path called the rewrite tensor pointer to try to make sure the backward compatibility. It means that even if user run this kernel on Ampere, it can still safely be run because there are some compiler passes to try to lower the make pointer back into the ordinary pre-hopper API. Yeah, that's something like that. And here are some very concrete examples, and we can see that on the left side is the Lex API, on the right side is the new API. We can see that there are differences very clearly. And with the new API, it becomes a little bit simpler for users to write their Triton kernels. And we can even make it more simpler because we can just eliminate the boundary check logic. Compared with the previous slide, we can see that there are some conditional checks to make sure when we are loading some data out of the boundary, we should make sure it's correct. But because the hardware already supports the boundary check natively, so we can rely on the hardware to do that. That can make our kernel even simpler. Yeah. And the next one is a new API for automatic optimization. The key design principle is that we don't want the user to be bothered about the optimization things because it's a little bit complicated to write some producer consumer code. At least for now, we want to automate the process. So user just need to specify a flag. Person of called the enable optimization to be true. When it's enabled, and we will do the optimization. Logical group, such as the epilogue, the prologue, and the commutation. And in theory, we want to execute them in parallel as much as possible. With that, we can hide the data latency as much as possible to achieve good performance. This is super important for new hardware because the gap between the mass instructions and the data instructions are becoming more and more apparent. And yeah, so how do we use the hopper on for Triton? And currently, the hopper feature is not turned on by default because there's still something ongoing there. And so you need to explicitly turn on hopper feature by yourself, but it's not very complicated. Actually, there are two major flags there. One is the enable TMA. You can just enable the TMA feature. The other is the enable MMV3, which is enable the hopper specific tensor call instruction there. And also there is the enable optimization and the number CTA. These two perf knobs can be used to enable hopper features. So relatively, it's easy for user to try hopper feature by themselves. Okay, so next I will talk more about some details. Let me cover this one. Yeah, it's a big room. And for Hopper to support that, we actually make some big changes with the data design, and also we introduce some new paths. And here is a very straightforward flow for Triton to lower from the Python level to the binary level. I will not cover the detail here because I suppose you folks are familiar with that. And to make sure this flow can work for Hopper, we need to do several things. First one is that we need to enhance the Triton's layout abstractions. And the layout actually is the core concept of Triton because it describes the mapping relationship between the data elements to be processed to the computation thread there. So it's very core for Triton. So for Hopper, because we have the CGA support, we have a new tensor call instructions. So we need to enhance the layout encoding, layout abstractions to support these new things. And also, we need to introduce some new operations to support Hopper specific features. For example, for barriers, for Hopper, there are some new barriers there. So we need to introduce some new operation to represent this barrier operation semantics. And also to support the TMA, we introduce some new data loading and store operations there. And for tensor call operation, because for Hopper, the work group MMA actually is asynchronous between instructions, not the synchronous instructions. So we need to introduce the .async operation instruction there. And for optimization, we just need to introduce some produce-consumer related operations to make sure we can represent these semantics. And this slide shows something about the organization of the path pipeline because the Triton compiler, so path is very important. And I will not talk too much detail there. The key thing is that there are two major sets of path pipeline. One is without optimization. The other is with optimization. So there are some slight difference there. Let me pick one or two paths as an example to show some details. One important path is plan CTA. And this path, the motivation is very clear. We want to minimize the layout conversion as much as possible because the layout conversion is expensive. When you do the layout conversion, it means that you might need to write the data to some intermediate memory and try to reshuffle and make sure it's compatible with the consumer instructions. And that will bring some memory overhead. And especially with the introduction of CGA in Hopper, it seems to become more complicated. So we have that path. The principle of the path is that we will firstly analyze the R sequence. Yeah, we will analyze the R sequence and try to locate a key operations and assign a layout to this key operation. And then we will do some propagation, like the coloring algorithm, to make sure all the operations in the R sequence can get their corresponding layout to minimize the layout conversion. That's the basic logic. And the next one is the automatic optimization, and this also is an analysis path in which we will just analyze the AR sequence and decompose the sequential AR sequence into several subgraphs, and then map each subgraph to the corresponding work group, which can be executed by different hardware. With that, we can just make them execute in parallel. And to support Hopper, also, we need to enhance the backend, and as mentioned before, because the Hopper is moving very, very fast, so there's still some gap between what community support and what we want. So here we just enhance the backend to provide some wrapper for the Hopper-specific PTS instructions. Hopefully, in the future, some of the work might be merged into the community repo, but it's not our current high priority. Okay, next I will talk something about the performance, and because it's very important for us, let me show some performance numbers. And let me explain a little bit about performance background. So here we just benchmark the IP16 gem kernels, and there are two sets of bars. The left bar means with split K shapes. The right bar means without split shapes. Split K actually is an important technique to operate kernels. It means that usually for gem kernels, we try to distribute the workload across the M and N dimension and distribute into different cities to try to parallel the workload. But when the GPU have more and more SMs, and when the M is not small enough, there might not be enough workload to be distributed across the M and N dimension. Oh, sorry, I'm time limited. Oh, yeah, let me quickly. So we need to split across the K dimensions. That's why we do that. And when we do the benchmark, we don't have enough bandwidth, so we didn't include the Triton split kernels. All the Triton already support that. Based on that, you can see that on the left bar, the gap is bigger than the right bar. But by integrating the Triton split kernels, the gap will be smaller. So currently, there are relatively around 25 to 30% gap between the Triton kernels to the cuBLAS kernels, and this is for all the important problem size, not just a square shape, also includes some small shape there. And we also have some more fine-grained plot here, and on the left, on the x-axis, we can see that is a shape ordered by their performance, and on the y-axis is a relative speed up. We can see for some problem size, Triton is still better than the cuBLAS, but for some problem size, it's relatively worse than cuBLAS, which is also quite similar along with what Phil said before. And also here is some performance for several memory-intensive kernels. We can see that for Vector-Z and Softmax, the performance is relatively decent. Okay, so I think I finished most of the major content, and let me just conclude with some plan for the future. There are several things we plan to do by working with OpenAI as a community. The first one is that we will focus on the performance optimization for web kernel because it's very important for Hopper. And next one is that we want to turn on the new feature for Hopper by default. So ease the effort of user to use Triton. The last one is that we will keep optimizing some important kernels such as flash attention and others. And that's all my presentation. Thanks for time. Yeah.
Thanks, Jun. So for our next talk, we have the AMD backend bringing Triton to AMD GPUs. Again, I'll get the presentation set up and we can get started.
Test.